Hey, last time out we investigated a problem that incorporated friction in it, and we found out that the work done by friction was negative and that friction took away some energy from the system. Let's take a deeper look at what kind of force friction is and what kind of work it does. So in this example we have a block that I'm trying to push in the horizontal direction, a distance of 15 meters, by applying a 400 Newton horizontal force as shown. Let's say I move the box at a constant speed. So what does constant speed mean? Constant speed means that we have zero acceleration. Zero acceleration then implies that there is no net force, no resultant force due to Newton's second law. If there is no net force, then there is no net work, because work is directly related to the net force, right? So this is what constant speed means. What is our question here? The question asks, what is the work done by friction? Alright, so in trying to move this block, what is the work that friction does on it when I try to move it a distance of 15 meters to the right? Let's go ahead and, as usual, start with our free body force diagram. Choosing our axis as follows: plus x plus y. We have the block, we have the horizontal force on it applied by me to be 400 newtons. Of course, we have the weight of the block, mg. We have the normal force exerted by the ground on it. And what else? We have the friction force. When I try to slide the block to the right, the friction will oppose that sliding and act towards the left. We want to find what is the work done by friction. Now, since net work is zero, we worked out in our previous problem that net work was the total work done by all the forces in moving the block in the horizontal direction. So since there is no vertical motion, no vertical forces do any work, so the only work done is the work done by me and the work done by friction. So net work is actually work done by me plus work done by friction. However, since there is no acceleration and no net force, this means no net work, so net work is zero. If this side of the equation is zero, that means that the work done by friction is equal to the negative work done by me. Okay, this is the consequence of moving the block at a constant speed. So if I can find the work done by me, then I will automatically be able to tell what friction is, what the work done by friction is. Then let's find out what the work done by me is. Remember, work has the following formula: the magnitude of the force applied times the magnitude of the displacement, which is the distance, times the cosine of the angle between the force and the displacement, cosine of theta. Alright, using this, the work done by me would be the magnitude of the force that I apply, which is 400 newtons, times the distance I successfully moved the block to the right, which is 15 meters, times cosine of the angle between F and the displacement. The force is to the right, displacement is to the right, both are horizontal, hence the angle between them is 0 because they are parallel. Cosine of 0 is just 1, so this comes out to be 6000 joule. If the work done by me is 6000 joule, then the work done by friction is equal to negative 6000 joule. All right. using this equation. Now let's say that this was point A, and at the end of my 15 meters, let's call that point B. Now let's tell ourselves that I move the same block applying the same force, but now to move from point A to B, I follow a rectangular or a longer path, which looks like this. If this is A and this is B, the old path was just a straight line from A to B. This was a distance of 15 meters. The new path, however, I will choose is a longer path which will follow a rectangle looking like this, such that the starting point and the ending point is the same, but I follow this red path. This is 15 meters since this is a rectangle, and this is, let's say, 5 meter and 5 meter. So I travel a distance of 10 meters extra. So now my distance covered is 25 meters. Now what is the work done by friction in this case? We want to check if the work done by friction has changed from when we moved in a straight line from A to B than when we moved from A to B in a rectangular path. Let's follow along the same directions, finding the work done by me first. Work done by me is equal to 400, still the same magnitude of the force, times the distance. Now what is the distance? The distance has now changed. The distance, let's write it in red, is now 5 plus 15, which is 20, plus 5 is 25 meters. That's the new distance. Alright, cosine of theta. Now what is the cosine of theta? Well, it is still 0. Cosine of 0, right? Because the force is still horizontal, the distance covered is still horizontal. Alright, then this comes out to be 10,000 joules. Therefore, the work done by friction is negative 10,000 joule. This is significantly different than our new friction. So we can see that if we follow a longer path, the work done by friction would be more. Alright, so this shows us that the property of forces like friction is that they are path dependent. Forces such as friction are path dependent. So the work done, this means that the work done by friction is dependent on the path you choose to go from a starting point A to a finishing point B. So any different path you take, the work will be different. These kinds of path dependent forces are given the special name of being non-conservative forces. And only such force that we will talk about in this course is friction, or if you come across air resistance, which is like air friction, and all other forces that we will study like gravity and spring force, they are what is called conservative forces. Alright, so conservative forces, on the other hand, are path independent. They're path independent. So conservative forces like gravity and spring forces, which we'll meet shortly, they only care about what is your starting point and what is your finishing point. They don't care about which path you take. And so this is a difference between friction and forces like gravity and spring forces. Alright, now we have mentioned that gravity is a conservative force, meaning that gravity, the work done by gravity is path independent. So gravity, when doing work, doesn't care what path you take to get from one point to another. So for example, if this is your starting point A and this is your finishing point B, gravity doesn't care whether you go from A to B following this blue path straight up or this red path, which is at angles shown, and we'll investigate if that's true. So the question asks, what is the work done by gravity, Wg, for each path? So let's first consider the blue path, path 1. For path 1, let us draw a free body diagram for the block that has already left the ground. So the free body diagram will have an axis plus y. There is no horizontal motion in this case, so we don't care about the plus x-axis. So what are the y forces? Well, all the forces that are acting on this block are vertical forces, and if we are ignoring a resistance, which we are in this case because we're investigating only forces like gravity, conservative forces, so the only force acting on this is mg, or the weight of the block. Okay, now let's say that the block is actually 2 grams. All right, so this is actually, we can write as 2 grams, so 2 over 1,000 kilograms times g. So this g is different from this g. This g is the weight, which is the acceleration due to gravity, so because this is a force. All right, anyways, let's move on, and this is the only force acting on it. So the work done by gravity in this case, and remember that you are moving the block up, so the delta x points up along the y-axis, your weight points down along the y-axis, so they're anti-parallel to each other, the force and the displacement. So the work done by gravity in this case is the magnitude of the force, which is 2 over 1,000 times 9.8 times the distance. What is the distance? The distance is, for path 1, it is 3 meters, 3 times cosine of the angle between the force and the displacement. So since they're anti-parallel, the angle is 180 degrees. So cosine of 180 is, as we have seen before, -1, and this comes out to be -58.8 joule, and this negative implies that you're actually working against gravity. So the work you do is positive, the work gravity does is negative. All right, so this doesn't mean that work is a vector, it just means that gravity is taking away energy as you move it up. So this is why this work is negative. Let's now think about path 2. Let's use the red pen here. Path 2. Now for path 2, again let's draw a free body diagram. What are the forces on it? This is the block of 2 grams, so it will have a weight 2 over 1,000 times 9.8 g, and then the path it follows is in this direction, so it doesn't have any other forces on it. So for our purposes, let us just go ahead and draw the path to make our lives easier on the free body diagram. Usually when we don't do that. All right, so this is the path it follows, delta x. This is not any force, this is the path it follows. All right, so this is the force, this is the path, and with the horizontal, the path makes an angle of 45 degrees, and given to us is one side of the path, the vertical of the path is given to us to be 1.5 meters. Now since the angle is 45 degrees, we know that this is an isosceles triangle which has 2 sides equal. So if one of the angles is 45, another angle is also 45, and these 2 sides are equal, so this is also 1.5 meter, and this is a right angle. All right, and this is a similar, this is the exact same triangle, the upper triangle. So we have 2 isosceles triangles, so this path follows 2 parts, One is this triangular path, another one is this triangular path. So to find the total work done by the gravity following this path 2, we have to consider both of these triangles. All right, if we do that, then we have the work done by gravity as 2 times 2, because there are 2 triangles, 2 parts of the same problem, 2 times what the work done by the one path, let's say this path. So in this path, what is the work done? Work done is the magnitude of the force, which is the weight, 2 over 1000 times 9.8 times the distance it moves. What is the distance it moves? The distance is this hypotenuse of the right angle triangle. All right, this distance would be nothing but when you apply Pythagoras theorem. So if you do that, delta x is equal to square root of 1.5 squared plus 1.5 squared. This comes out to be 2.12 meters. So we have the distance to be 2.12 meters, and the angle, cosine of the angle between the force, this force, and this displacement. What is this angle? Well, we know this much is 45. The angle between the displacement and the horizontal is 45, and we know that the angle between the force and the horizontal is 90 degrees. So the total angle is 90 plus 45, which is 135 degrees, and that is the angle between the force and the displacement. So we have a cosine of 135 degrees. All right, this is the work done by gravity when it follows path 2, and this whole thing comes out to be negative 58.8 joules. This is exactly the same as before when we followed path 1. This shows that gravity is indeed a conservative force, and so it is the work done by gravity is path independent. You can choose any path to go from the same initial point to the same final point, but you will end up with the same work done by gravity. And these kinds of conservative forces has an energy associated with them. So for gravity, the energy associated with it is known as gravitational potential energy, or GPE for short. And any kind of conservative forces will have a corresponding potential energy to it. For gravity, that potential energy is gravitational potential energy. So let's reiterate, conservative forces only care about the initial and final position of the object. It doesn't care about what path you choose to go from the initial position to the final position. Every conservative forces that we will come across will have a corresponding potential energy associated with it. The potential energy is the energy based on the position of an object. Since conservative forces only care about the positions, the relative positions of the object from starting point to the finishing point, or they have a potential energy associated with them, which is associated to its relative position, and it is denoted by U, capital U, or more precisely as delta U, because when calculating potential energies, we are only ever able to calculate changes in potential energy, because potential energy depends on not an absolute position of an object. The position is always relative between an initial point and a final point. So whenever you compare initial and final points in any situations, you are actually measuring changes in potential energy. All right, so we will always measure, whenever we talk about finding potential energies, we'll always measure changes in potential energy. Now, associated with gravity, a conservative force that we have just come across, we have the gravitational potential energy, as was mentioned, which is denoted as delta U sub capital G. This is equal to, or small g, it's up to you. I write capital G just to differentiate it from the acceleration due to gravity. This is equal to mg delta y. M is the mass of the object, g is the acceleration due to gravity on near the surface of the earth, which is 9.8, and delta y is the change in the relative position of the object between an initial point and a final point. So delta y is yf minus yi. All right. So often, since this is a vertical displacement, gravitational potential energy is concerned with vertical displacement, vertical positions. This will often be called a height. Okay. So for example, if you want to calculate the gravitational potential energy for the example we just considered, in moving from A to B, this block covered a distance, a total distance of 3 meters. 3 meters is its height, and the mass is 2 grams, so 2 over 1000 kilograms. Remember, all of these must have SI units so that the energy comes out in joules, which is the SI unit for energy, times g, which is 9.8 meters per second squared, times 3 meters, which is the height or the y displacement, yf minus yi. You can consider yi to be 0, the starting point, and yf to be the final point, which was total of which was 3 meters. So if we calculate that, we will see that it is a positive 558.8. Now if you remember, this is the same number as the work done by gravity. So in effect, potential energy, the gravitational potential energy, is the same as the work done by gravity. All that means is the more height you give an object, the higher you take an object, the more potential energy it has, the more gravitational potential energy it has, and the more gravitational potential energy it has, gravity will put in or try harder to bring it down. So we can say that the more potential energy you have, the more work gravity puts in to bring it down. All right, so they're in effect the same thing. So we have to be careful to not ever write potential energy and work done by potential energy in the same side of an equation. So in the beginning of our study with energies, we put this fact up in the context of the law of conservation of energy, when we stated that energy can neither be created nor be destroyed. So energy in the end is always conserved. The initial energy of the universe is still the same. Say this is the final time, we still have the same energy that the universe started with at the Big Bang. So we can now qualitatively put it, like we always do in physics, in an equation form, and we call this equation the work energy theorem. Let's go step by step. In step 1, we realize the relation between work and energy. Already we know that work, the total work done on something, is the change in energy of that system. All right. Now we have learned two sorts of energies, which is, one is kinetic energy, energy associated to motion of an object. Anything moving will have kinetic energy. And the other is potential energy, anything, the energy based on position, anything that has a relative position, say between the ground and some final point in the vertical direction, will have gravitational potential energy. So this is equal to the summation of all those energies, the change in all those energies, kinetic and potential, is equal to the work done on the object by non-conservative forces, by friction. So if you don't have a non-conservative force, then the kinetic energy is equal, the change in kinetic energy is equal to minus the change in potential energy. But when you have non-conservative forces, the work done by non-conservative forces is equal to the summation of the changes in each of these energies. NC, by the way, means the work done by non-conservative forces. Now we can take these changes out and expand them out. So delta K means Kf minus Ki. Delta U means Uf minus Ui, the change between a final point and an initial point. We want to take all these initials, Ki's and Ui's, to one side of the equation. So we add those Ki's and Ui's to both sides, and we end up with Ki plus Ui plus W and C is equal to Kf plus Uf. Ki plus Ui is the energy I start with. Kf plus Uf is the energy I end with. If you don't have a non-conservative force like friction, then the energy you start with is equal to the energy you finish with. So energy is whatever energy you put into the system, or you had before you started actually, you will end up using up that same energy. You can't use any more than that. But whenever you have non-conservative forces like we do in practical life, we always have friction when we want to move some things, then this is the amount that is taken away or put in externally into the system. So this is the energy put in or taken out of the system. You can, this whole equation is given the name of work energy theorem. This is the holy grail when it comes to solving problems using energy concepts. All right. So if it doesn't make sense in an equation format, think about it like this. Say you have 10 bucks, you don't have any other money, but you saw an item on Amazon which is 12 bucks. So you really need to get it, but you only have 10 bucks. You can't spend any more than that. What you can do is you can call a friend and they can lend you 2 bucks. So you have started with 10 bucks. You can only end up with that amount unless you borrow some 2 bucks from a friend. So now that you have borrowed 2 bucks, that you have put in some energy into your system or some money into your pockets, you can go ahead and then spend 2 bucks. So in summary, you can only spend what you have. This is the basis behind all of this work energy theorem. If you don't have enough energy, you can't go ahead and finish that system. You have to put something in, or if there are non-conservative forces in the surroundings, they will take some energy out. All right. I hope this discussion made some sense, and in the future lectures, we'll investigate examples on how work energy theorem actually works.